Hello and welcome back to another episode of Math with Sohn. Today we are going to be talking about volume continuity and Bernoulli's equation. So this is Bernoulli's really big equation. And the volume continuity is the simple one. It's A1v1 equals A2V2. All right. Now with that equation, we have to understand that this just represents the volume per second. All right. And no matter what, if we have water flowing through this pipe right here, flowing through this little section and then flowing through this section, the amount of water has to remain the same in every single section. Okay? You can't have more water going through here than you have in the little section. Now, it will change the velocity though. All right? Because here we have a bigger area, the velocity would be slower than right here where we have a smaller area. If the area decreases, the velocity has to increase. So area decreasing, the velocity would have to increase, which makes sense because if the area is going down, that water has to speed up to be able to accomplish getting rid of the same amount of it. All right? So that is with horizontal pipes though. And it is also assuming that we have laminar flow and no turbulence. With all of these problems, laminar flow is smooth and non-turbulent water where it is just no friction essentially. It's just the perfect water that flows through the pipe that doesn't lose any energy and it doesn't have any bubbles or turning or turbulence or anything, nothing like that. All right, we got a volume continuity problem that we're going to try out, and then we're going to explain a little bit with Bernoulli's and say why it's important. So in a water jet cutting process, the water hose has a diameter of 0.5 centimeters and uses this volume of water in 20 seconds. We are going to determine the cross-sectional area of the hose. All right. So A1v1 is equal to the volume per second. Now the reason that is because area is typically like length times width, and velocity is distance divided by time. So we would have length times width times height, distance, divided by time. That's why we got volume divided by second here. So we have the volume, we have the seconds, and I am going to keep it in centimeters. I'm not going to worry about meters for the time being because I don't think we need to worry about anything. It says centimeters per second, centimeters cubed, all that stuff. So, we have centimeters. I'm actually going to do part B first. We got the volume divided by 20. That is what it's asking for. Volume divided by time. So that would be 300 divided by 20, which is equal to, let's simplify that down. 300 divided by 20 is equal to 15 centimeters cubed every second, which is part B. How much volume is used every second? Done. All right. What is the cross-sectional area of the hose? Well, the cross-sectional area of the hose is going to be equal to this, the volume per second. So we have A1v1 equals 15. All right. So A1, we don't know. V1, actually, we could figure out the cross-sectional area without doing any of that stuff. We got 0.5 centimeters right here, so that would be 0.25 centimeters would equal the radius. This is an easy question. That would just be 0.25 pi r squared. So pi, I'm using 3.14, times r, 0.25 squared is annoying, 0.196, I'm going to call it, rounding that up, centimeters squared. Okay. What is the speed of water from the hose? That was what I was attempting to do. I didn't think that it would have so many simple questions in leading up to it. That is where you would have to take A1v1 equaling V15. All right, we just found out A is 0.196. It's actually 0.19625. 0.19625 times V, velocity 1, would equal 15. So we just divide, and we figure out this is going through pretty quickly. When we divide, we end up with a velocity of 76.4 centimeters every second. So about a meter a second. All right. Now, why is this important? It's important because when we're talking about the the continuity equation where you have A1v1 equals A2V2, a lot of times when you're dealing with Bernoulli's, you won't be provided one of the velocities, which is very important when we're talking about Bernoulli's equation, because if you don't know one of the velocities, you would have to use A1v1 equals A2v2 to maybe solve for the velocity to be able to fulfill the rest of the equation. Now, while we have Bernoulli's here, it's important to recognize and understand that this is used and is a good representative of potential energy and kinetic energy of the water, and then this would be like the initial pressure, and this would be the final pressure. All right? And all of these things work in conjunction. If you increase the velocity, odds are that you are going to decrease the pressure. If you increase the height, you're probably going to lose either pressure or you're going to lose velocity. It all counteracts each other in a variety of different ways. And if you just know that the equation has to be balanced, if you increase one thing, you got to decrease one of the other two. If you increase two things, you definitely have to decrease the third. And it would have to equal the other side. All right? That's going to do it for this one. Until next time, everybody, stay positive, and I will see y'all later. Bye.